So, imagine opening a set of Russian nesting dolls, right?
Okay, I'm with you.
But like, before you can open the next one in the sequence, you have to run this incredibly complex safety check. You have to inspect the wood for scratches, check the paint for chips, maybe even measure the humidity of the room.
That sounds exhausting, honestly.
Right. And if just one of those checks fails, you can't just stop and say, hey, this doll is broken. You have to carefully, painstakingly put every single doll you've already opened back together.
Oh, wow.
Yeah, perfectly, before you can even report the error. It's a terrible way to unpack anything.
It really is. I mean, you'd end up spending significantly more mental energy just managing the dolls than actually looking at what is inside them, you know? The core task is totally eclipsed by the bureaucracy of checking for failure.
Exactly. And that is the perfect analogy for what we're looking at today in this deep dive. I was reading a developer blog by a programmer named Ang the other day, and they perfectly diagnosed this exact architectural nightmare.
Oh, the Haskell post, right.
Yeah, the post was published on May 11th, 2026, and it's called Notes on Haskell Programming, Part 132, The Staircase versus the Pipeline.
It's such a great read because anyone who has ever built a complex workflow, whether you're writing software or setting up a data pipeline or even just designing a daily workflow, has run into this trap.
Ang calls it the staircase of case. So for everyone listening who has ever felt overwhelmed by complex, nested processes, this deep dive is going to reveal a really universal structural pattern for handling errors gracefully. Okay, let's unpack this.
Let's do it.
Before we get to the beautiful, elegant solution that Ang finds, we really need to understand why this staircase is such a universal trap.
Yeah, the staircase of case is just a wonderfully evocative name for a structural anti-pattern that plagues, almost every software engineering team at some point.
It's everywhere.
It is. And to truly grasp why it happens, we have to look at what Ang's code is actually trying to accomplish. So Ang's building this command line tool, and the specific function acting as the engine for this tool is called parse CLI.
And it's doing some heavy lifting. It isn't just one simple action. First, it has to parse the command line arguments the user types in.
Right, which can easily fail.
Exactly.
Yeah.
Then it has to validate those arguments to make sure they aren't completely nonsensical. Then it parses a text file, converts that text into a fully formatted ebook,
And
and
finally, it tries to automatically open that new ebook file on your computer.
right. And every single one of those sequential steps carries a very real risk of failure. The user might type the wrong command, right? Or the text file might be corrupted.
Or the ebook converter just crashes entirely. And, in languages like Haskell, which is heavily focused on purity and strictness, you can't just throw an invisible exception and hope some other part of the program catches it later.
Like you might in Python or Java.
Exactly. Haskell treats errors as explicit data. The language basically forces you to deal with the possibility of failure right then and there.
So as a developer, you write a case statement. You run the first step, parsing the arguments, and you explicitly write out the cases. Like, in the case of success, move forward. In the case of failure, stop and print an error.
Which makes total sense for one step. But Ang has a whole sequence of steps. So the physical shape of the code begins to warp.
Moving how?
Well, because step 2 relies entirely on the data from step 1, you have to place the case statement for step 2 completely inside the success branch of step 1.
Oh, so you're indenting.
You're indenting heavily. First case opens, did it succeed? Yes. Indent the code, start the second case, did the conversion work? Yes. Indent again, start the third case for opening the file.
And it just keeps going.
Right. With every new step you add to your process, your code marches further and further to the right side of your monitor. It physically shapes itself into a staircase leading down and to the right.
JavaScript developers call that the pyramid of doom, right? Or callback hell.
Yeah, exactly the same structural trap. Ang specifically mentions dreading this exact shape forming on the screen. The code currently just prints processing txt file name and then descends into this nested nightmare.
But let's pause here because if the computer can read this code just fine, and it obviously can, why does the physical shape of the text matter so much to the developer?
Because code is read by human beings orders of magnitude more often than it is written by them.
That's a great point.
When you build a staircase structure, your happy path gets completely fragmented.
The happy path being the path where everything actually goes right.
Or the actual sequence of events you want to have, parsing, converting, opening. But human eyes have to zigzag back and forth through layers and layers of error handling just to piece together what the function is fundamentally trying to achieve.
So the cognitive load simply to read your own work just becomes enormous.
Massive.
It's like trying to read a novel where every single sentence is followed by a lengthy legal disclaimer about what to do if you misunderstood the sentence.
That is a perfect way to put it. You lose the plot entirely.
So if the staircase is so universally hated and it creates this massive cognitive tax, why do developers keep falling into the trap in the first place? Is it just the easiest way to write code on the fly?
It really is. It's a direct, unfiltered translation of linear human thought into syntax. When we build a sequence in our heads, we naturally think, okay, first I do A. Did A work? Yes. Now I do B.
We naturally micromanage the sequence.
Exactly. The problem is that while linear thought works for, say, making a sandwich, it does not scale. When a system grows complex, that micromanaged structure just collapses under its own weight.
So there has to be an escape hatch. If the staircase is the trap, Aang eventually finds a way to flatten it out into a clean vertical pipeline.
Yes, and this is where it gets really interesting.
Right, because this involves bringing in something called the Monad Transformer Library, or MTL, and a very specific tool called ExceptT. Now, I have to say, the author admits that even with AI assistance, reading the documentation for this library was brutal. The terminology is incredibly intimidating. Why do these elegant functional programming solutions often come wrapped in such intimidating terminology?
Well, the intimidation factor is very real, and it stems from Haskell's lineage. The language is deeply rooted in abstract mathematics, specifically category theory.
Right, so you got all these math terms.
Exactly. The terms you see, monads, transformers, applicatives, they are mathematically precise, but they are incredibly hostile to a working programmer who simply wants to convert a text file and not have their program crash.
Yeah, we definitely need to translate that academic weight into something a bit more tangible for the listener. The source text talks about run ExceptT and wrapping the individual steps inside this ExceptT block. What is fundamentally happening under the hood there?
Think of a monad, conceptually, as a highly programmable semicolon.
A programmable semicolon, I like that.
Right. It is a structural pattern that tells the computer exactly what background rules apply between one line of code and the next. In Haskell, you have different monads for different contexts.
Like what?
Well, you have the I/O monad, which handles the messy reality of side effects, like talking to the file system or printing to a screen. And you also have the either monad, which handles the context of failure.
Returning either a left containing an error or a
Right.
containing the successful data.
Exactly. But parse CLI needs to do both of those things at the same time. It has to talk to the file system to open the ebook, which is an I/O side effect, and it has to handle the possibility of failure, which is the either context.
But I'm guessing you can't just mash those together.
You can't. Standard monads do not naturally compose with one another. You cannot just mash I/O and either together out of the box, and that is where the transformer comes in.
So what's fascinating here is how the transformer bridges that gap.
What's fascinating here is that a monad transformer, like ExceptT, is a mechanism that actually stacks these behaviors. It takes the error handling capabilities of either and weaves them seamlessly into the side effect capabilities of I/O.
So it's running the side effect and the error checks simultaneously in the background.
Yes.
So Aang wraps the parsing, the converting, and the file opening steps inside this ExceptT structure, specifically within a do block. And the code completely flattens out.
It goes from a messy nested staircase back to a simple readable vertical list. Step 1, Step 2, Step 3. The visual clutter of the error checking is entirely gone.
It really reminds me of setting up a massive chain of dominoes. In the staircase model, you are nervously walking alongside the falling dominoes, ready to dive and catch one if it tips the wrong way, manually evaluating every single collision.
Right, micromanaging every fall.
But in the pipeline model, you just let them fall. You install a sophisticated circuit breaker, that's the ExceptT block. If any single step fails, if it returns a left error, the circuit simply breaks.
The execution halts instantly.
Instantly. Completely bypassing the rest of the steps, and it drops straight to a single error-handling case block at the very bottom.
The delegation of responsibility is what makes it so elegant. You are no longer hard-coding the failure management into the steps themselves. You are trusting the structural environment to manage the flow of state.
So if everything succeeds and results in a cart, right, the program hits the bottom and prints success.
Yep. And if it trips the circuit breaker anywhere along the way, it outputs error, followed by the specific message that caused the halt.
But wait, if ExceptTime acts as this universal safety net, how does it know how to catch errors from all these different functions? The command line parser might have been written by one developer, the ebook converter by another, and they probably return completely different error codes.
Oh, they definitely do.
So it can't just be magic. You can't just throw a universal wrapper over disparate pieces of code and expect them to snap together perfectly, right?
You absolutely cannot. A smooth pipeline requires highly standardized pipes. And this introduces a significant architectural challenge that Ang had to solve.
Standardizing the tracks.
Exactly. To make the ExceptT block work, to allow it to manage the flow of errors for multiple different functions, those individual functions must be reshaped. They need to speak the exact same language when they fail. They need unified type signatures.
Right. Looking at the source, Ang had to force every single step in the process to return a generic string as its error.
Just a basic text string.
And Ang notes this was done specifically to be compatible with a tool called opt_parse_applicative. That's the library handling the command line arguments, and it defaults to dealing with invalid arguments by throwing a string.
So to make the pipeline connect, everything else had to be coerced into returning a string too. We can see the specific refactoring Ang had to do to achieve this.
Yeah, look at the open ebook function.
Originally, it had a type signature of IO. The empty parentheses just mean it performed an action opening the file and returned nothing of note. It essentially assumed it would succeed.
But to fit the pipeline, Ang had to change that to IO, either string.
Right. Now, it performs the action, but it explicitly returns a string if it fails, or nothing if it succeeds.
But here's where it gets really interesting. Ang is changing a specific error, like a pando error, from the convert to ebook function.
Yes.
Originally, it returned a highly specific custom error type called either pando error file path. It was rigorously designed to tell the system exactly what mathematical or structural thing went wrong during the document conversion.
And Ang changed it to either string file path.
Yeah.
They discarded the precision of the pando error type in favor of plain text.
Doesn't dumbing down the error into a generic string mean we lose incredibly valuable debugging information just for the sake of making the code look prettier?
I mean, that's a very fair question.
If you have a pando error, you can write code that programmatically inspects the exact species of the failure and maybe attempts a specific recovery. If it's just a string, it's just dumb text. Aren't we making the underlying system technically weaker?
Well, think about the implications of that trade-off, because you are touching on one of the great philosophical divides in software engineering. The balance between local precision and global flow.
Local precision versus global flow.
Exactly. Yes, locally, the convert to ebook function lost its rigid pando error identity. You sacrificed deep programmatic introspection, but globally, you gain an overarching architecture. Think of the Industrial Revolution.
Oh, like standardized parts.
Exactly that concept.
Right.
Before standardized threads on screws, a machinist crafted a custom, highly specific screw for a custom hole. It was a perfect, locally precise fit.
But terribly inefficient.
Right. If you wanted to build an assembly line to mass-produce complex machines, you couldn't rely on custom fits. By standardizing the thread sizes, by saying every single error in this entire pipeline, no matter how complex, will simply be expressed as a text string, you lose the bespoke nature of the failure.
But you gain the ability to process the entire assembly line using one single universal machine.
Yes, the ExceptT block.
And considering this is a command line tool where the ultimate destination of an error is usually just getting printed as text to a human sitting at a terminal anyway, a string really does the job perfectly.
The context is everything. You trade a level of rigor you weren't actually using for a massive reduction in cognitive load.
Okay, so Ang wrestles with the math jargon, standardizes the error types, and gets the pipeline flowing beautifully. The staircase is demolished.
Completely flattened.
But stepping back to look at this freshly refactored code triggers a much wider realization for the author. This deeply technical, seemingly isolated effort to clean up a Haskell script leads to a cross-language epiphany.
It's a phenomenal moment of structural resonance in the blog post. Ang looks at the new Haskell code, utilizing run ExceptT in the do block, and suddenly realizes it bears a striking similarity to a completely different programming ecosystem.
Elixir.
Elixir.
Specifically, Elixir's with statement. Ang points out that both languages, despite having completely different syntaxes, allow for this exact same happy path flow, where execution immediately halts upon encountering the very first error.
The author provides the Elixir code side by side for comparison, and the architectural mimicry is undeniable. In Elixir, you write with OK, tokens .parse content.
And on the very next line, you execute the conversion, and the next, you open the command. It is a flat vertical list.
And then at the bottom, just like the consolidated Haskell case block, Elixir has a simple do io.puts success, followed by an else block that catches any error from any step and prints error with the string.
It's basically structurally identical.
It is. And we really need to underline how disparate these two environments are. Haskell is statically typed, purely functional, and heavily tied to academic category theory.
Right.
Elixir is dynamically typed, built on the Erlang virtual machine, and explicitly designed for highly concurrent, fault-tolerant distributed systems like telecom networks. They do not share a direct evolutionary lineage.
It's like discovering that two completely isolated ancient civilizations, separated by oceans, invented the exact same type of archway for their buildings.
That's a beautiful way to think about it.
They didn't talk to each other, but the raw physics of trying to hold up a heavy stone roof led them both to the exact same structural solution. So, what does this all mean for you, the listener? If these patterns repeat across languages, does that mean learning the concept of the happy path is actually more valuable than learning the specific language syntax?
What's fascinating here is that this structural solution actually has a name in the broader systems design community. It is called railway-oriented programming.
Railway-oriented programming. I like the sound of that. Break that down for me.
So imagine your program is a railway network. The happy path is the main track. Every function parsing, converting, opening is a railway switch.
Okay.
If the function succeeds, the train stays on the main track and proceeds to the next station. But if a function fails, the switch diverts the train onto a secondary parallel track.
The failure track.
The failure track. And once you are on the failure track, you bypass all the remaining stations. The train rolls unimpeded all the way to the end of the line, straight into the central air handling depot.
So both Haskell's ExceptT block and Elixir's with statement are just different syntaxes for building these exact same two-track railway systems.
Precisely. When vastly different languages converge on the exact same paradigm for handling sequences and failures, it reveals a fundamental truth about system architecture.
It's universal.
It proves that isolating your error handling from your core logic isn't just a neat trick for making code look pretty. It is fundamentally aligned with how human beings best process logical flows.
So we started at the bottom of a messy staircase of case, took the monad transformer elevator up to a clean pipeline, standardized our error types along the way, and realized we had built a universal structure shared by entirely different languages.
It is a deeply satisfying refactor to read about. But before we conclude this deep dive, there is one final, incredibly subtle detail buried in Ang's source text. It's easy to gloss over, but I think it fundamentally challenges the idea of perfect software architecture.
You caught something in the metadata.
Yeah. When Ang was updating the package.yaml dependencies to bring in the monad transformer library, they had to explicitly specify the version limits of the core Haskell library, which is called base.
Okay, and what did it say?
The code specifies that the base package must be greater than or equal to version 4.2, but it must be strictly less than version 5. It is written mathematically as base equals 4.2 and in 5.
Wait, strictly less than version 5. So Ang is hard-coding a ceiling into the project.
Think about the fragility of elegant solutions. This beautifully readable, perfectly flattened pipeline, this magnificent archway we just discussed, is completely reliant on external libraries interacting flawlessly.
Right.
The developer has explicitly locked this perfectly clean code out of any future version 5 of the language.
Yeah.
Almost certainly because major version updates introduce breaking changes to these exact underlying structures.
So the code is perfect right up until the moment it isn't.
I want you to consider that ticking clock. What happens to this perfectly clean, beautifully standardized happy path pipeline when the foundational language inevitably updates to version 5?
It breaks.
Is the pursuit of perfectly clean code always haunted by the ticking clock of software updates that might break the very libraries that make it possible? You build the perfect railway, but you have to build it on top of a fault line.
That's a sobering reality check. You abstract away the messy details of error handling, you standardize your parts, you achieve the perfect flow, but your perfect system is completely tethered to the shifting tectonic plates of the libraries beneath it.
It really makes you appreciate the constant, delicate balance between writing beautiful architecture today and ensuring long-term maintenance tomorrow.
It really does. And that is where we will leave it for today. So for everyone listening, look closely at your own projects and your own daily workflows. Are you building a fragile staircase, checking every single step and burying your main goal in a mountain of micromanagement? Or is it time to standardize your errors, build a two-track railway, and let the process flow? Keep untangling those nesting dolls.